Welcome to my talk about Java streams at JCON. It's my first talk at JCON, and I'm very glad that there are so many of you here. And two remarks that I need to say before. First, I would like you to ask your questions at the end, because I'm afraid to run out of time otherwise. And also, if I'm silent for 15 seconds up to 1 minute sometimes, I'm still alive. It's just a chance for you to read the slide and think about it without listening to me. I once noticed that I can do this all three at the same time. But before we start, I would like you to use the chat and tell me which Java version you use. That would be very interesting for me. Just enter numbers. Okay, wonderful. Yeah, 11 and 17. Ah, some 8s. Okay, wonderful. Nothing smaller than 8. Great. I see. That's nice. That would be the numbers I would expect. And some even 18, but nobody 19, I guess. That was released today, if I'm not wrong. Okay. And second question, if you rate your experience with Java streams from 0, I've never heard of Java streams, to 10, I know Java streams better than all OpenJDK developers. Which rating would you give yourself? Type just a number into the chat between 0 and 10. Okay. Okay, that's interesting. So I notice everybody of you has has made some experience with it. And that's nice, because we can now use it for this talk. First, I will introduce myself and tell you what I hope you already know about Java streams. Then I will give you some personal recommendations. After that, I will talk about one of the biggest problems for stream expressions, and those are side effects. And I will continue with describing what and how streams are. Many streams expression examples will follow, which show you when to use streams and when not, in my opinion. And besides, I will remind you to the divide and conquer technique you all know, I guess, which also can be used for splitting up what I call stream monoliths, so long stream expressions. Moreover, I show you some stream expressions, how they can evolve with an example. And last but not least, I will give a short summary and, of course, answer your questions. I hope you enjoy it. So who am I? Well, I'm Michael, 38 years young. I live in Munich, Germany. And yes, that's where the Oktoberfest is. And I have recently started working for Yambit, and I like it. It has interesting project, nice colleagues, great events, many more for me. And maybe it's good for you as well. I also have graduated in computer science in 2012, and I've learned Java since I began my study in 2005. I've worked 9 years in full-time and contributed samples to JMH and C-Stress, which were accepted. In my leisure time, I've played improvisation theater for the last 12 years now. And improvisation theater, that's just theater without a script. So this means everything is completely spontaneous and improvised. A very useful skill, as you can imagine. And I'm also a proud uncle of 2 cute nieces. You can find me on GitHub and Twitter as Mirwaldt. So I hope you've noticed this talk is a talk for Java developers who already know the basics about Java streams. I guess you all wonder what I mean with the basics. And here's the answer. Well, I hope everybody of you should be familiar with the Java Lambda syntax and method references. Also, you should know functional interfaces like supplier, consumer, function, predicate, and operators. Last but not least, you must have used the intermediate operations like filter and map, and the terminal operations like collect and reduce. They're very, very common. However, you don't need to know all intermediate and terminal operations for this talk. So let's start with my recommendations. First of all, you should limit the number of operations you use for stream expressions. I've noticed that 99% of all my stream expressions that I write need only at most 5 operations. You can prefer 3 or 4 if you want, However, I would avoid the magic number 7 or the famous Miller number or above values. Recent psychological studies imply that the capacity of our working memory is definitely lower than 7. It's rather 3, 4, maybe 5, but not more. And also just use one operation per line. Venkat Subramanian once said there is only one reason why you wouldn't do that. And this is you hate your colleagues and you don't want them to understand your stream expression. And I think that's a good, funny answer because there's no good reason not to do it. And also avoid side effects whenever you can, because they make stream expressions hard to understand and introduce subtle bugs very often. We will cover what's a side effect and how they can be avoided in just a moment. Also, double check whether you really need to use for each, because better terminal operations often exist. I will show you an example. Stream expressions are like diagrams for me. If you overload them with details, they become useless because you cannot understand them anymore, what they tell you. Good diagrams focus only on one goal and only include all relevant details for this goal. They leave out all other details to point out the relevant details. And the same applies to stream expressions, at least for me. If you need to think a lot about how to write a stream expression, you and your colleagues might also need so much time to understand them later. So this can indicate that a stream expression might not be a good solution. However, it's only a rule of thumb with some exceptions, of course. Remember divide and conquer. You can split up stream expressions the same way as long methods. You can introduce explaining variables with intermediate results for parts of your stream expression. I will show you later an example if I don't run out of time. And I know it sounds trivial. If you are not sure whether a stream expression is good or not, just try it out by one solution with a stream and one without a stream and compare them. It's not much work in most cases. And last but not least, don't forget you can always ask your colleagues what your stream expression does. If the colleague can tell you it within 30 seconds, that's fine. If they give up after 5 minutes, throw it away. It's not worth your and your colleagues' precious time. So that was a lot, I guess. What about having the first 30 seconds to think about that? Okay, let's continue. What are side effects? Well, there are two typical ways to introduce side effects into your stream expression. This is the first one. Have a look on this example for 15 seconds. Okay, as you can see, we're with acceptable inputs in line 7, with the inputs from the stream expression between lines 5 and 7. And this is so flawed. Why? Well, first, this stream expression actually hides its goal to create a list of acceptable inputs. And second, there already exists a terminal operation. It's collect, and it does what you actually want in line 11, a list of acceptable inputs. So the stream expression in the lines 9 to 12 reveal its goal in opposite to the other one. You might argue it's so obvious in this example, but don't forget it must not be so obvious in your production code. And what about this side effect here? Have a read of this example for the next 15 seconds. I'm pretty sure everybody of you has once seen a lambda with a hidden state. And once again, you can ask me, what's the beef, sir? Well, wouldn't it be nice if such side effects were so obvious when they exist? And that's the point. You don't always know whether a lambda which somebody passes you has got a hidden side effect or not. And would you really always like to expect one? I hope not. Imagine for a moment you get the predicate pass and you use it here, and it is used at the same time in another lambda expression as well. This gets very ugly then. And apart from that, the state for lambda destroys the layout for the stream expression by the need of 4 lines instead 1. And let's don't talk about parallel streams here. What about being pragmatic instead? I'm pretty sure you all noticed the second expression in line 8, 9, and 10, because here we just use the index of method that gives us the index. And of course, index of is a linear search. However, how many elements do we have? More than 10,000? If not, it won't matter. And if you have got many elements, you might have them sorted so that you can use binary search, which is also very efficient. So please just be pragmatic. So let me share some observation about Java streams I made. Stream expressions are expressions, not programs. And expressions are short where programs can be very long. So keep the expressions short. Streams are pipelines, but no replacement for iterators or loops. Iterators and loops are still very useful. And that has not changed since Java streams were introduced. Also, streams are one-dimensional. They often don't work for multidimensional stuff like multidimensional arrays. And streams must read from a source, but should not change it, except for each, which sometimes changes the source. And also be careful with views in your streams like map.entry, because if you change them, very strange things can happen, and you should avoid that. Also be careful with empty streams. If you don't create many of them and you don't call the intermediate operations on them, then don't mind it. However, if you have created many empty streams, then you should need to know this. Streams are unfortunately not smart enough to know whether they don't need to create a pipeline for that empty stream or not. So if you create many streams, check whether they are empty before you use them. Just call the splitterator method and the method estimate size on the return splitterator. If estimate size returns your value above 0, then the stream is not empty. And then you should create a new stream with stream factory methods of the class stream support, which accepts splitterators. Keep in mind, splitterator is a terminal operation and streams can only be used once. That means if you call splitterator on a stream, you cannot reuse the stream anymore. You need to create a new one. Oh, that was a lot. So have a 30 seconds again. Good. So far about the theory. Let's have a look on examples. First, I show you examples where I consider stream expressions very useful, and then we get to help. Have a look on these 2 examples for the next 30 seconds. Okay, I give a short explanation for them. Well, first, you see here the killer app for stream expression I would call queries. As you see it in the first example in the lines 1 to 5, because you can see it, that's a typical query. First, we just filter which elements we want. For example, we just select the range of first letters from J to Z in line 3. Then we map it, for example, to uppercase in line 4. And last but not least, we just group them, for example, by the first letter in line 5. Now the second example. Imagine we need a conversion of names, for example, from a module name to a camel case name, as in lines 6 to 10. First, we split the module name into tokens. That means we split by the dash character separator in line 7. Then we skip tokens, for example, the first 1 in line 8 with the skip method. After that, we map tokens. For example, we map tokens to tokens with the first letter to be a capital letter in line 9. And last but not least, we join all tokens. So that means we concatenate all tokens simply in line 10. And if necessary, we just add a suffix without the stream, a suffix like process also in line 10. And I think this is very handy and very useful. Next example, please ignore just for a moment that very oversimplified reg expression for positive ints. Just have a read for the next 30 seconds. So why do I show you this example? Well, you see in both letters the all match method. And some developers, I think, have not yet discovered this cute little terminal operation, all match, any match, and non-match for checks. Imagine a method that passes and sums positive ints like in the example. You might want to check whether all elements in the parameter in a strings are positive ints which can be passed before you do it. You can use a regex expression to check all elements by all match first, as in line 2. And if all elements are positive ints, you just pass and sum them in the lines 3 to 5. If, however, one element is no positive int, you just find it in the string expression in lines 7 to 9 and throw an illegal argument exception in line 10. Another nice example is this. It's about merging two sorted maps. Have a read for the next 15 seconds. Okay, I hope it was not too complicated for you. Let's have a look on it together. You see two sorted maps in line 1 and 2, and we use here the map off method, where the key, the value, the key, the value, this is the order of the entries, or the keys and the values. And for example, the left map in line 1 has the entries key 1 mapped to value 3, key 2 mapped to value 1, and key 3 mapped to value 4. I hope you see it. And now let's merge them. We could use some loops, but here the stereo expressions are more useful because we can just create a stream of those two maps in line 4, flatten them to a stream of all entries of both maps in line 5, and collect them to a new sorted map in line 6 to 9. If both maps have an entry with the same key, the entry with the minimum value is selected in line 8, as you see. This applies to the entry with the key 2, which gets the value 1 because it's the minimum of 1 from the left map and 3 from the right map. And the best, it also works for more than 2 maps. Now we get to hell. I'm the devil, welcome. No, just kidding. have a look on both examples for 30 seconds on one example, this one example. So I'm pretty sure everybody noticed what this code is about, because we want to remove here all third elements in line 9. So that means the first third element, then the sixth element, and so on. However, we cannot really do that with a stream expression because we will face most probably a concurrent modification exception. But why do we need? We have still the useful iterators, and they can remove elements. And also we need a kind of counter variable to count whether it's the third element or not. And that would be too difficult with the stream expression. I'm pretty sure most of you who studied computer science, math, or physics, or other subject might remember how to transpose a matrix. For all the others, a matrix is rather a table of numbers, and if you mirror the elements on the diagonal from left top to right bottom, then you get the transposed matrix. And as an example, the matrix in lines 10 to 12 is a transposed matrix of the matrix you can see on your numpad on the keyboard without zero. So have a look on this example for 30 seconds and try to understand it. Okay, you see in line 1, there is the two-dimensional array, which is our matrix. And then we use two nested loops. The first loop in line 2 to line 8, and the second loop, the nested loop from line 3 to line 7. And what we actually do is just that we iterate in the first loop over the columns, over the rows, and in the nested loop, the second loop, on the columns. And we just iterate over the left elements below the diagonal and just swap them with the mirrored numbers. And we don't need a stream for that. Okay, this is my horror example. I've seen it in several variants, and I must always vomit when I see it, frankly speaking. Some of you all have already guessed it. It's about Fibonacci numbers. You remember? It was the sequence where you start with 1 and 1 and sum the last two predecessors. That means 1, 1, 2, which is 1 plus 1, then 3, which is 1 plus 2, 5, which is 2 plus 3, and so on. So give it a try for 1 minute. If you give up, don't feel ashamed. I think it doesn't. It's absolutely okay with that strange example. So may I ask you in the chat, who of you has given up just enter a Y, and if you really think you have understood it, then an N into the chat, please, as a kind of feedback. I would really be interested. Yeah, I see many Ys. Okay, wonderful. Why is it wonderful? Because then you don't do such, sorry to say it, bullshit. And why is it bullshit? Well, there are two answers. The first answer is short, the other answer is long. Let's first start the short answer. Well, it's this. Just have a read on that. I'm pretty sure most of you understand it within 30 seconds. I would even bet. Okay, why is this here so easy? Well, we only need 5 lines here, from line 2 to 6, and it's just a plain old for loop with a very boring long array and a little exciting modular operator, and that's all we need here. Now let's get to the long answer. The long answer is this stream expression tries to emulate a loop in a pretty clumsy way, in my opinion. First, we abuse the stream to generate values from 3 to n for an implicit loop counter in line 2. So that's not the data, that's a counter variable we need. Then we need to switch to boxing in line 3 to enable the needed reduce method, which is our next victim, because there are several different reduce methods. This reduce method here has 3 parameters: identity, accumulator, and combiner. The identity is the first value, the accumulator are the following values, and the combiner combines them in case that you have a parallel stream. So it merges the intermediate results to the final result. And here we smuggle a long array with 3 elements, our actual data, into it as identity in line 4. And then we abuse the accumulator to calculate the next Fibonacci number in each time in line 6. As it must return something, we always return the same one long array in line 7. And last but not least, we need to pass an unused combiner in line 9. Isn't that ugly? Go. Now let's look on a stream monolith. It's a too long stream expression. Here you can see a stream expression which finds the top 10 of the most used words in a text. Have a look on it for 1 minute. So once again, can you help me with feedback? Have you understood what the stream expression actually does in detail? Just enter our Y if you think so. Please enter an N if you are not sure. Just into the chat. Okay, I see many N's, and that's not a problem because I will show you something where you can really see what kind of intermediate results you have. The point here is that you can use divide and conquer as well for streams. Or in my words, you just split the stream expression into smaller parts with which you can deal. How you can apply that to a long stream expression as well. How? Well, have a look here. those are the first two parts. Have a look on them for the next 30 seconds. Okay, who of you helped this explaining variables to understand what the intermediate results are? Just a Y and a N once again. Nice. You see, two explaining variables and everything gets easier to understand. And now we still missed the third part. And here it is. I must point out, who of you knows what records are? They were introduced in Java 16. Just a Y and a N, please. Okay, I've seen two N's, or three N's, no problem. They're whether a new feature, and I think they are immutable final classes with only the fields in the class header, and with the default equals method, hashcode method, a default constructor, taking all fields, and accessor methods for all fields. And the class header directly follows the name of the class in line 1. So you see that long frequency and the string word. Those are the two fields of word entries. I hope this helps you. And if you wonder why they were introduced, well, they were introduced to enable pattern matching in switch expressions in future Java versions in the project Ember. Just have a look on this example for the next 15 seconds or 30 seconds. So you see here, we use that word entry for temporary entries in line 4 to flatten all the entries from the words by frequency result in line 2, so that we can pick 10 word entries for only one word, instead of 10 entries from words by frequency, where one entry can have more than one word. If that's not clear to you, well, I will make it clear now. When I gave this talk here once to Chuck, somebody made me aware of a problem. My top 10 of words is actually biased. And why? Well, consider this famous children rhyme, some of you might know, in lines 1 to 5. It's just the first and the last lines. And if you then look on the result in line 6 to 6, 7, and the result in line 8, 9, you will notice that for the 10th word, there are just two words, the word spider and wiggled, with the same frequency of 12. And what I do in my top 10 is actually just I pick out the first one, spider, and just ignore the other ones, which is a kind of bit arbitrary. And actually, it would be a better solution if, in this case, I just put them both into the top 10, even if it is not a top 10, but a top 11 then. Or let's say it's a top 10 plus, because I don't know how many more elements I will have. So how can we do that? Well, this, what I showed you before with divide and conquer, has another big advantage, because you can rewrite your stream expressions separately from the other ones. And this allows me here, in this case, just to use the first two frequency maps and then just to calculate a different result. However, first, when I tried it, it was a really miserably failure for me. Try to understand this. If you give up, don't feel embarrassed. It's quite natural. The solution is terrible. but it helped me to find the better solution. Just another minute, okay? Okay. First of all, what actually led me to this bad solution? Well, I put it in bold letters. I used a stream of entry sets, so a stream of entries. And it led me to the wrong way, because now I first had to map those entries to single entry maps, so that I was able to inverse the key and the values in line 2. And in line 3, I do something completely weird. First, I just give him a supplier for a sorted map. You see here the tree map with the reverse order in line 4. And now here comes the very ugly hack. I use result put all, because it doesn't return anything. Because this here is an accumulator which doesn't return something. And you will get compiler errors otherwise. And in this, I have a ternary operator where I check whether I need to add more entries or not. And if I need to, then I just put all that one single maps into it. And otherwise, I just give it an empty map, which is really ugly. And I was able to do it better. And maybe you should have a look on this. And the biggest difference is that I now start with the key set instead of the entry set. Just have a minute to understand that. Okay, I somehow feel that we run out of time. What's different here? Well, and why is it better? Well, first of all, who of you knows what headmap does? Can you just enter an Y or an N if you know for what headmap is used? Okay, I see some no's. Okay, it's not a problem. I'm pretty sure that you can remember that lists have a method called sublist, where you can pass the first and the last element, index, and that you get a view on that list. And that also exists for maps, for sorted maps. And there is a submap, where you can say the first, the last key. However, there's a shortcut, because head maps, they just always start with the first key, and you only have to pass the last key. And for tail map, it's the opposite. And here we just use it in a smart way, because in line 2, we just create a view with the first key, then with the second, with the first and the second key, then with the first, the second, and the third key. So we create a view that gets larger and larger. And then we are able in line 3 to check whether we have already 10 or more words in it. And if so, we just make a defensive copy to decouple it from the result from the view on the map, the original one. And last but not least, we only need the first one that fits. So all the other head maps, we are not interested in it anymore. And that we tell in line 5 with the find first. And in case that we don't get at least 10 words, well, we just use inline 6 or else and just create a defensive copy of all of the map. And I think that's much better, and I like that solution more. Okay, now my summary. Remember, you should set a limit like 5 operations per expression, and you should use 1 operation per line. It's easier to read. Keep in mind that stream expressions are only useful when they're easy to understand. Also, avoid side effects, like writing from inside the stream to outside the stream, or stateful lambdas. They are hard to understand and introduce subtle bugs often. And split stream monolith into pieces and use explaining variables for them. And keep in mind that streams are one-dimensional pipelines with one goal and no replacement for neither iterators nor loops. And the most important, please use them only where they are useful, but not just everywhere. So that was my talk. Thank you for your attention. You can find the slides and the examples on this link here. I will post it into the chat in the next moment. And I would be happy to answer your questions. I hope you have some.